Hello everyone, this is Anukriti Sethi and I am a third year undergraduate student doing my BTech in Engineering Physics from IIT Roorkee. In this video, we will discuss about the potentiometric error detection method. So let's begin. In this experiment, we will investigate how a pair of potentiometers can be used to create an error detector for a position control system. We will measure the linearity and range of the potentiometers and analyze the error detector's behavior with both DC and AC excitation. So let us now have a look at the apparatus that will be used for this experiment, which includes a potentiometric error detector unit, a digital voltmeter, and a dual trace oscilloscope. So this is the setup that we will use for the experiment. We have the oscilloscope and the potentiometer error detector PED1 unit. There are two potentiometers. The first potentiometer, which is called the control potentiometer, and the second potentiometer, which is called the reference potentiometer, and both of them are connected in parallel with each other. Then we have the theta 1 and the theta 2. These are the angular spans for the potentiometer, and we can change these angles using these knobs. And similarly for theta 1, we can also adjust theta 1 using this knob. Then there is this switch using which we can switch between AC and DC excitation signal. There is a carrier which is internally connected with the demodulator, and we also have this unit where we can ground the oscilloscope, and this is our oscilloscope, which is used when we have the AC excitation signal. And these are the connecting wires which we will be using for our experiment. So let us now dive into the theoretical aspects of this experiment. So to begin with, what is a potentiometer? It is an electromechanical transducer which converts angular or linear displacement into a proportional electrical voltage. Potentiometer is an important component of a feedback position control system. They are also used in open loop system for the purpose of monitoring the angular position of a shaft. When a reference voltage is applied across the fixed terminals of the potentiometer, the output voltage measured at the variable terminal is proportional to the input displacement. The rotatory potentiometers are commonly available in single turn or 3 by 10 turn varieties. These have restricted motion with mechanical stops at both ends. These potentiometers are normally wire wound for long rotational life but have finite resolution. The resistance, tolerance, and linearity are also excellent. From this figure, we can see that the output voltage ET may be written as Ke into theta t, where theta t is the shaft position and Ke is the constant of proportionality. Ke is written as voltage applied upon maximum angular span. The use of two potentiometers in parallel, supplied from the same source, enables a comparison of two shaft positions, a reference shaft and a control shaft. The output voltage, taken across the variable points of the two potentiometers, may be expressed as Ke into theta 1 minus theta 2, which can be written as Ke into theta e. This is the schematic diagram of a DC position control system which uses a pair of potentiometers as error detector. In this system, the DC motor rotates in a direction to align the potentiometers and to minimize the error. A system similar to this is also possible using AC excitation of the potentiometers, AC amplifier, and a two-phase AC servo motor to drive the load. The difference between the DC and AC position control systems essentially arises from the features of the amplifier and motor types used. There are various advantages of AC systems over DC systems, such that AC amplifiers are free from drift and the transformer coupled output allows single supply operation. Also, Two-phase motors having no commutators and brushes are inherently more robust and maintenance-free. So let us have a look at the case of the AC excitation signal. In this case, if the AC signal is given by Ks theta e into V sine omega ct and the sinusoidal angular error is sine omega st, then the output Et may be represented as a suppressed carrier signal which can be given by Ks upon 2 into V cos omega c minus omega s into t minus cos of omega c plus omega s into t. This is then passed to a demodulator where it is multiplied by the carrier signal of amplitude V dash. This is done to extract the direct information from the signal. We then get the output as Ks into V dash upon 2 into theta e multiplied by 1 minus cos of 2 omega c t. So to remove this 2 omega c component, we then pass it through a low pass filter so that we get the final output as Ks V into V dash by 2 into theta e. This may then be amplified by a DC amplifier before feeding to a DC motor. So, what are the various steps involved in this experiment? Let us have a look. We'll first switch on the setup and we'll make the proper connections as shown here. We'll connect the resultant voltage of potentiometer 1 and 2 with the digital voltmeter. We'll set theta 2 to 180 degree. This can be any value as this is a reference potential reference theta, and we'll vary theta 1 and note down the corresponding voltage readings. We'll observe that as we increase theta 1, the value of the voltage decreases. We'll continue varying it. This will soon reach a negative value. And for every small intervals, we can note down the reading of the voltage. Now, for the AC excitation signals, we have to change the connections. We'll now also connect the demodulator and then we'll connect the demodulated output to the digital voltmeter so that we get the demodulated reading. And we'll also connect the resultant voltage with the oscilloscope so that we get the AC readings on the oscilloscope, as we can observe here. On setting theta 2 to 180 degree and on varying theta 1, we can observe that the digital voltmeter gives us the demodulated output, and here on the oscilloscope we get the signal wave as well as VRMS, Vmax and other details. So that was the procedure of this experiment, and we get both the AC and the DC readings from the potentiometer. On plotting a graph between the potentiometer output and the shaft position, we can make certain conclusions. The linearity of a potentiometer may be defined as the maximum percentage deviation of the output voltage from its ideal value. This may be better appreciated from this graph between the potentiometer output and the shaft position. Again, the range of the potentiometer indicates the angle through which a proportional output is available in the potentiometer. So we get a linear graph from the readings obtained of various voltage output for various angle positions, and this experiment successfully studied the performance of a potentiometer based angular position error detector. So that was all on potentiometric error detection. Hope you gained some knowledge from this video. Thank you.